Hello, I'm Doug McNeall. Welcome to Mostly Climate, a new podcast series from the Met Office. You might be familiar with our existing series, Mostly Weather, which explores all things weather-related. That series has also covered climate, but we thought a subject as important, pressing and wide-ranging as the science of climate deserved its own dedicated series. Don't worry, Mostly Weather will continue to delve into the wonderful world of weather. Check out the latest episodes on our SoundCloud channel. Now, joining me for Mostly Climate is Annie Schultz, science communicator here at the Met Office. Thanks for joining Mostly Climate, Annie. So what does working as a climate science communicator involve?
So my team focuses on getting the relevant bits of science to the people who need it and in a way that they can easily understand and use.
Can you give me some examples of the people you talk to?
We primarily talk to government departments, and they really need to hear about the science that's relevant for policy. So, for example, what impacts does climate change have so they can adapt to those? But we also talk to the general public interested in climate science and all the researchers as well.
That's great. And it's one of the things that we're trying to do with Mostly Climate, I guess. So that's really good. So thanks, Annie. In the coming months, we're going to be looking at a host of climate science stories, from early scientific discoveries through to the latest research and global efforts to predict our changing climate. And we're also going to be counting down to COP26. Annie, can you fill us in on what COP26 is?
Firstly, COP, what is it? That is short for Conference of the Parties. It's the name of the international UN conference dedicated to climate change and how countries are planning to tackle it. So it's happening later this year in November in Glasgow under the joint presidency of the UK and Italy. It's going to be a huge event. At least 196 governments will be there and other key organizations working in the world of climate.
This year's COP will be particularly important. Do you want to tell me why?
Although COP has been happening every year for 25 years, is the first COP since the measures from the Paris Agreement have taken place. Quick reminder, the Paris Agreement is a landmark in international climate action. It's a legally binding treaty for countries to limit global warming to below 2 degrees and preferably 1.5 degrees compared to the pre-industrial time. So in short, COP26 will be the first opportunity since then for countries to come together to review their plans to achieve that common goal.
So there's lots to talk about on climate and particularly on COP26 over the next few months. But in this episode, we're going to look at how scientists combine data from all over the Earth system with computer models to try and form a picture of our climate and the challenges that those scientists face in trying to make sense of really complex systems. So where are we in our current understanding of climate? A few weeks ago, a report was published by a group of scientists known collectively as Future Earth. The report, 10 New Insights into Climate, outlines the latest scientific findings and what impact the changing climate will have on society. Here's Future Earth spokesman Eric Pill.
We've gone through some of the most fundamental aspects of the climate system. One concerns the equilibrium climate sensitivity, how sensitive the climate is to carbon dioxide. Also, there's data on emissions from permafrost, when we see that including something called abrupt thaw, the emissions from permafrost could double in this century. We're also looking at the response of the land sink. Ecosystems on land pull up about a third of the emissions that we emit as humans. So we're looking at how that is changing. Then we have some insights relating to the impacts to see that water stress and mental health impacts are among the things we need to consider when it comes to the impacts that climate change has on humans. We also look at what we've seen related to the COVID crisis, the effects of restrictions. We're looking at urban electrification, so electrifying cities. And we're also looking at climate litigation, so going to court over climate cases has changed our understanding of how we deal with these kind of issues in the legal systems.
Eric Pill there. Annie, as I mentioned, Future Earth is made up of a number of scientific organisations. How has the Met Office contributed in its own special way to this latest report?
Our scientists have contributed to one of the key new climate insights, which is really about our work on improving our understanding of the climate through computer modelling, particularly in one area that we call decadal forecasting.
Okay, decadal forecasting sounds interesting. Can you explain what that is?
So here at the Met Office, forecasting is done in a range of time periods. You've got nowcasts that tell you what's going on right now, weather forecasts that tells you what's happening in a few days ahead, and you've got climate projections that will tell you what the climate will be like at the end of the century. Decadal forecasting sits somewhere in the middle. It looks at what the climate of the next few years might look like.
So I usually think of climate as what you expect and weather is what you get. So the weather is a particular thing that happens on a day, but the climate is all of the things that might happen on that day. What allows us to make those decadal forecasts?
For decadal forecasts, we really need what we call climate models. So what are climate models? Essentially, they're a computer program that simulates our climate. It really is just a set of mathematical equations for a computer to solve. And these equations represent the physical laws behind the behavior of the different elements of the climate system, for example, the atmosphere or the ocean. We've been doing that for over a decade now, and recently we've actually been recognized as the World Center for this by the World Meteorological Organization.
And I gather you've been talking to one of the key scientists at the Met Office Hadley Centre, which is the climate part of the Met Office.
Yep, that's right. I was lucky to chat to Professor Adam Scaife, who leads the Met Office's work on predicting the climate months to years ahead. And he told me a little bit more about why decadal forecasting is important and how it's recently improved.
We're all familiar with the weather forecast, the weather forecast on your TV every evening. They've been going since the 50s using big computers. In recent years or recent decades, we've had climate projections, and we know the stark warnings that come from those in terms of climate change. And that's really looking at the century timescale or the multi-decadal timescale, where you're talking about the statistics of the weather rather than the weather on a particular day. So you've got to take the sources of predictability, if you like, the sources of information from the weather forecast, and that's really saying, what is the weather doing today? What is the ocean doing today? And combine that with the stuff that goes into the long-term projections, which is about things like the changing greenhouse gas levels over the coming century. And it's putting those two together that are needed for this very important middle time scale.
How do they add value?
Weather forecasts are a fantastic triumph of science that have been around for a long time, but we haven't been able to say much about the seasons or few years ahead. And actually, for many people, whether they work in business or in government, that middle time scale is the key one, because it's that time scale that people make a lot of decisions on. For example, planning for drought or international aid. There is a whole myriad of possible applications.
So going into exactly what was featured in the review, decadal prediction, how have they evolved over time?
Every year, about 10 centres around the globe make forecasts, and we can bring those together and we can look at what they're saying. But of course, we don't necessarily trust that prediction unless we know how good it is at predicting past events. And so we do a lot of analysis on retrospective forecasts. And what's highlighted in the 10 New Insights paper is that actually, when you put enough forecasts together, so enough, we call it an ensemble of forecasts for a given period, then you can predict regional temperature, regional rainfall.
I was wondering if decadal predictions can be useful at all in the context of extreme weather events.
In 2017, we published a study where we examined winter monthly rainfall for the UK. And we asked that question, what's a reasonable worst case scenario? And the answer that popped out from that analysis is that about 1 in 3 years, we expect a new regional record in the UK for winter monthly rainfall. This was published in 2017. And then in February 2020, we had the first monthly regional rainfall record in the UK. So there's another application of the decadal forecasts. They give you many estimates of the current climate.
So that was Professor Adam Scaife talking to Annie there about improved decadal predictions. So that's really interesting stuff. I thought Adam highlighted some great insights, particularly into heavy rainfall events in the UK and the extremes that we might see in the future. Can you explain a bit more about how that's done, Annie?
The method that Adam talked about here is really quite revolutionary. It basically allows us to calculate the risk of extreme events happening today, even if they may have never happened before. We're looking at very heavy rainfall causing severe flooding, heat waves causing lots of disruptions. We do this by generating thousands of virtual simulations for the current climate, which makes it possible then to calculate the risk, even if there's very little observations available. So why is this really useful? It is extremely useful because A, it helps prepare for these worst case scenarios that are now probable, but it also helps show that the impacts of climate change are not a faraway thing into the future, geographically remote from us. We now have numbers to show that more intense, frequent extremes can happen now here in the UK.
That's really super useful. So I've often thought about the distributions of weather because you only really feel the extremes, and then by nature those extremes are rare. You might not understand how that distribution has kind of shifted underneath you, and that you're basically setting yourself up for a real surprise in terms of the amount of rain that might fall in one place or a particularly extreme heat wave. And I think we saw that, I remember back in 2003. In 2003, there were sadly a lot of deaths in the southeast of England and in Paris because we saw an extreme event that was basically unprecedented. So I think this method really offers a great way of warning against those unprecedented events. So, Annie, has this method been applied to things other than rainfall?
Yeah, actually, it's interesting you were mentioning heat earlier on. That's exactly what a study that was published last year looked at. So how likely are we to see extreme heat in the UK? That study found that there is now an 11% risk each year of exceeding the hot summer temperatures that we saw in the summer of 2018, which was the joint hottest summer on record in the UK. Now, that might not seem like a big number on its own, but if you actually look back at what that risk was back in the 60s, it's increased rapidly. Back in the 60s, it was less than 1%.
That's really interesting. So a huge increase, was sort of a tenfold increase in the risk there. I often hear it's better not to think of, last year or 2018 as the hottest year in the UK of the last century, but maybe to think of it as one of the cooler years over the coming century. And you really get to understand what the next century might look like. A lot of my work here at the Met Office involves testing models and trying to figure out how we can make them better. But what if your model is missing a potentially important part of the climate puzzle? We'll hear about the second climate insight from Gustav Helius, Associate Professor of the University of Stockholm. Earlier, he spoke to mostly climate producer Claire Nazir and explained how climate models are only just starting to include data and processes on a key indicator and driver of climate change, permafrost.
Permafrost are areas that are affected by really cold climates where you have frozen ground all year round. So even in summer, if you scratch a little bit down into the surface of the soil will be frozen. It's a very widespread phenomenon. It's mostly found in Russia, Canada, and Alaska, but also in Scandinavia, other parts of the Arctic. There's a little bit of permafrost also in Antarctica, but that's quite limited. The total area of permafrost in the northern hemisphere is about 14 million square kilometers. So that's basically all of Europe times 3.
So this area locks in a huge amount of not only methane, but also carbon. Let's talk about 2020 and the Siberian heat wave. Not only was it record-breaking in terms of temperature, but the actual length at which the heat persisted was significant as well.
Permafrost has effectively been cooling the climate for millennia by slowly accumulating carbon dioxide out of the atmosphere and binding it in the frozen soil. And when climate warms, or when we have a heat wave, as we did this summer, the permafrost starts to thaw, and it can either happen gradually or it can happen very quickly. And I think that there's ample evidence that the heat wave that we saw this summer is unique, both the severity and the length that it occurred, and also we did see quite a lot of effects to the permafrost system.
So permafrost clearly is a significant factor in the regulation of Earth's temperature and atmospheric composition. But how far has permafrost data been incorporated into climate models?
We do have a set of climate models, not all of them, but several climate models that do include permafrost and that can simulate a gradual slow thawing of permafrost over time. And that starts to release more and more greenhouse gases. Now, this effect alone is very significant. Add to that, there is another type of permafrost thaw process, which we collectively call abrupt thaw processes, which is basically more localized landscape effects where the thaw happens a lot quicker. It can be triggered by a fire, it can be triggered by ice disappearing that leads to the formation of a lake, which makes the whole process go even quicker. It can also happen along coastlines, rivers, in slopes where you get something similar to a landslide where a big chunk of the landscape just thaws away very quickly. And what we have found is that if you add these processes together, these processes alone are almost as strong as gradual thaw that was already represented in the Earth system models. So basically, we have to double the permafrost impact to the climate going forward when we account for these abrupt thaw processes.
That's a fascinating new insight that Gustav shared here and shows how far we've come in representing the climate system in models. But it also highlights that models aren't perfect. Doug, your job revolves around improving them, right? So can you tell us a bit more about what causes their imperfections?
A lot of the climate models have traditionally come from weather models. So from the 50s back through to the present day, weather models were driving the technology and people were using the physics of the atmosphere really to make predictions on short scales. As we became more interested in climate, people started adding oceans and ice sheets and the land surface in terms of its biology. A lot of the shorter term variability is really driven by the physics of the atmosphere and the ocean. The longer processes are coming from the smaller and less well understood parts of the Earth system. And I think, one of the really important things there is that as you learn more, you understand how those processes change things like carbon budgets, for example. So how much carbon you can put into the atmosphere, say, through industry or through travel in order to hit a particular temperature target. We've also got to incorporate the fact that our models aren't absolutely perfect into our predictions. And I would say that that can still be super useful. If you give somebody a range, you say, look, things are going to get warmer by between this much and this much, and we're pretty certain or 99% confident that it's not going to get cooler, that can still be useful to a decision maker because they know they have to build their infrastructure in one direction. They have to account for it.
That makes me wonder, how is the information that all climate models produce fed back to be useful and inform governments and the rest of society?
Well, to try and answer that, I spoke to our final contributor, Kath Senior, who leads research dedicated to understanding climate change here at the Met Office.
My name is Kath Senior. I'm Head of Understanding Climate Change here in the Met Office Hadley Centre. I'm also a co-chair of the working group on coupled models within the World Climate Research Programme. First of all, most importantly, climate models are built on physical principles. So we use the equations of motion, we use equations of thermodynamics, and it's critical that we recognise that the physics behind the models is sound. Of course, we can't represent everything with the equations. The models have limited resolutions, numbers of grid points across the globe. So when we simulate the climate, we evaluate that against observations that we've got. So data from things like aircraft, from ground-based data, radars, for example, and most importantly these days from satellite data.
One of the things that I know we do is we compare our climate model with the climate models built and created by other modelling centres. Could you talk us through what they call the CMIP process, the Climate Model Intercomparison Project?
CMIP is a process that's been going on for about 20 years now, started in the 1990s. Its goal is to better understand past, present and future climate. What it does is it provides a common experimental design for our models, including both idealised futures and past, and also realistic future scenarios of where the world might go. And then international modelling centres, as you say, using a range of different models. And in the last phase of CMIP, we had about 40 international modelling centres with more than 100 different types of models involved. They can all use this kind of common platform, if you like, running the same experiments. And then we, the international scientific community, are able to use that information. That data is made available to people. We'll be able to use that information and, as you say, provide comparisons of the way the different models are evolving. And I think it's critical that policy is based on these best estimates from the broadest range of scientists across the world.
So it sounds like the models are helping to create a consensus position on what the science says. It's almost like you're looking for what do all the models say, or what do the vast majority of the models say, and therefore this is the thing that we're really sure is going to happen. Is that fair?
Yes, that's right. I think we're looking for robustness. If all the models are suggesting something and we understand the physical principles behind why that might be sensible, then I think that gives the scientific community very strong view that that is our best estimate of today. If there's a lot of uncertainty, then I think we absolutely have to say that, and that allows the decision makers to look at where the statements are robust, where they're not, and enables us to build good decisions based on those sorts of judgments, to know that the whole of the community is behind that all the scientists from different countries are in agreement. They've evaluated this broadest range of models and they've come up with these principles. I think is the only real basis for making those important world level decisions.
Cass Senior there talking about how useful climate models are to make sure that policy is underpinned by science.
This really brings us back to where we started, doesn't it? Showing us how climate models serve as the basis of climate science, but also climate negotiations, which will take place later this year at COP26.
That's right, and we'll be looking at how that happens in the COP26 process all the way through this series. But that brings us to the end of this first episode. I'm Doug McNeall, and my thanks to co-presenter Annie Schultz, to producer Claire Nazir, and to editor Adrian Holloway. Do join us again next time for another episode of Mostly Climate.